Another example of related rates. This one has a lot going on. I also took away that scaffolding that lets you know kind of what steps to do, because you got to do those on your own. And you have some freedom in how you do it. I do recommend, though, that you create a pattern. You visually represent it in the same spaces each time, because having that geometry in your head of where information goes is a great way to help you remember and get through this. So let's give this a read. A tank is shaped like an inverted cone with height 8 meters and radius 4 meters. Water is added at 4 meters cubed per minute. Find the rate of change in height when water is 6 meters deep. And look, there's already a picture of what this inverted cone looks like. So you can give this a try, but I want to, before I get too deep into it, I want to take a little aside for some geometry, because I'm guessing a lot of you don't remember a lot of stuff about cones. So let's just recall some volumes real quick. We already saw that the volume of a sphere is 4/3 pi r cubed. But if I wanted to do the volume of, say, a cylinder, that volume is going to be just the area of the circle. And then we're going to multiply. So pi r squared is that area. And we just multiply by the height. This is how volume works, right? If you're going to, the word is extrude. You take this circle and you extend it out in space. You just multiply that area times the height, which means that for a box, if I had some box here, see if I can draw a box. Okay, and I can find the area of that square, that is, say, the top and the bottom. So I don't know, maybe this is length and this is width, and then it has a height. Well, the area of that square is length times width. And then to get the volume, I just multiply by that third dimension, which is height. Okay, so same pattern if I want to make, it's called a prism, right? I take a circle and I extend it, or I take a square and I extend it, or even if I take a triangle and I extend it, we could play the same game with a triangle like that, make a triangular prism. I would find the area of the triangle, 1/2 base times height, and multiply it by that width. Okay, so hopefully that was a nice reminder. We have a cone here, and cones and pyramids are the same kind of adjustment to this. So if I had a cone, I take my formula for what it would be if it was a cylinder, and I just divide by 3, or I multiply by 1/3. Same with if I took any kind of a pyramid. So I'm going to do a square pyramid, right, that has a square base. If I was going to connect this up into a pyramid, it's going to be as if it was a box. Here's L, here's W, and then it's got some height. Right? This also has some height. Then this is going to be length times width times height, just as if it was a box. But we've taken away a lot of volume, and it ends up being 1/3. Okay, for both of these. Any kind of cone or pyramid, just think of a cylinder or a box and then divide by 3. The reason why a third is actually something you'll learn in calculus 2. It has everything to do with the fact that if I take r cubed or x cubed and I take its derivative, I get 3r squared. So that 3 magically kind of features in there when you try to calculate the volume in calculus 2. Okay, so that was just a reminder on the side. Some basic shapes that I hope you can remember and know. You definitely also need to know those diameters and radiuses and circumferences and all of that, as well as your triangles. Okay, so with that in mind, we already have a picture drawn. We probably need to label it a little bit more as well, but let's go ahead and have our given rate. The rate we're given. We've got a rate we want. Again, you don't have to, but try to be consistent with yourself. I think this makes it really clear to yourself and the reader. It looks like we're told that water is added at 4 cubic meters per minute. So 4 cubic meters, what is that measuring? Well, that's a volume. A cubic meter is like a box, a meter by a meter by a meter. So that's definitely a volume. So the change in our volume is equal to 4. But this is a little weird because I've got this cone but I've got water being added at 4 cubic meters per minute. And right about now my brain goes, oh, I really should go back and figure out this picture. So usually I start with a picture, but let's see if I can go back now that I realize there's something more going on. What's happening is I've got water in this tank. Okay, and so something very bizarre is happening, that this water has right. This water is only partially filling up this tank, but the tank itself has its own dimensions. So the tank has a height of 8. So the tank has a height of 8. And that's fixed. And the tank has a radius of 4. But somewhere inside of this cone is this smaller cone full of water. And realizing that is part of this problem. Saying, oh yeah, I've got a cone that's the tank, but it's not totally full. So the volume that's changing here isn't the volume of that whole cone, it's the volume of this cone of water that's filling it up as it gets higher and higher. And we want to find the rate of change in height. So it looks like we want dH dt. Now that 8 isn't changing. The vessel here, this tank, is not changing shape. What's changing is how deep this water is. So this is our H. Very cool. All right. So we want dH dt. And it says when the water is 6 meters deep, what do I do with that other 6? Where does that go? Well, that is telling us when we care about this dH dt. So when H equals 6. Okay, I really should label one other thing here on this cone. I hope you know what it is and you think about it, but let's go ahead and pretend I didn't know what that thing is and I forgot. And I'm going to go down to here are my variables. Looks like I have an H for height. Oops. I have a V for volume. I have a T for time. There's definitely one more I'm going to need, but let's just pretend I don't know what it is yet. If you think about volume here, you should figure it out pretty fast. So now I'm going to go and I'm going to say, let's find a relationship. Again, you don't have to label this relationship, but if you do it every time, it'll help you remember what to do next. So I need some relationship that's going to connect this dV dt and this dH dt. Well, if one of them is a V, it means we're looking for a volume. What on earth is the volume of a cone? Oh, that's going to be pi r squared, the area of a circle, pi r squared, times the height of that cone, all over 3 or times a third. 1/3 pi r squared times h. Normally the 1/3 is in front. Great. Oh shoot, I don't have an r anywhere. That's the variable I forgot. So r is my radius. And I should definitely label it on here. It's the radius of this cone. And you see why putting it on the diagram, labeling on the diagram is so important, because a lot of people are going to get confused between that 4 and that r. Okay, so don't be afraid of kind of moving on a little bit and then circling back if you realize, oh, I need to label a different variable to get what I want. Okay. Next up, let's take a derivative. So, some people are tempted to do some plugging in and solving right here. You can make some relationships between r and h right away if you want to. In fact, sure. Let's make our lives easier. We could implicitly differentiate this right now. We would need to do the product rule, and that would be okay. But let's go ahead and notice that we have this h equals 6. And so we could implicitly differentiate this to get everything, but I'm going to also need an r in there as well, right? I'm going to need to plug in for r. So there is some relationship between h and r I'm going to need to find out. Let's go ahead and try to find that out right now. This is a tricky thing. So if I know h, I actually know r. Kind of like before with the right triangle. If I knew one leg, I knew the other leg. So let's see if we can figure that out right on the spot. And this is the thing that's gonna jog some weird memories. I'm gonna go ahead and draw this as a triangle. And I'm gonna draw my tank as a bigger triangle. Oops, that's not an H and an R. We know what those numbers are. This is an 8 and a 4. And the magic thing about these triangles is they actually live inside of each other. They should have all the same angles. So triangles that have all the same angles, there's a word for this. It starts with an S. They're similar. Similar triangles. And similar triangles share ratios. There's lots of ratios I could set up for this. The one I'm going to do right now is we could say that r over 4 is equal to h over 8. It's the same scaling factor to get from this r to this 4 as from this h to this 8. They're just rescalings of each other. So as long as I put the same sides over each other, we are in good shape. And now I'm just going to solve. And I'm going to say, okay, it looks like r is equal to, multiplied by the 4, 1/2 h. Fantastic. What does that buy me? It means I can rewrite this as v equals pi 1/2 h squared times h times 1/3. And now I've just got a single variable. Almost always, if you have 3 or more variables, you can do this. And you can do it at the beginning, like this, or at the end. Okay? Up to you. It's usually easier if you see it to do it now, because now your differentiation will be easier. All right, just a heads up, similar triangles are actually quite forgiving. If I were to say do r over h is equal to 4 over 8, in the end I would get the exact same relationship. So it doesn't actually matter which way you set up these fractions for similar triangles, as long as you're consistent. Right, that's the same ratios across the two triangles. All right, let's clean up this a little bit here. We're in good shape. So this is going to be, I'm going to square the 1/2, so I get a 1/4, and I'm going to bring that 1/3 in front, so I get 1/12 times pi. So pi over 12, h cubed. Oh, that is so nice. All right, implicitly differentiate it. Whenever you do implicit differentiation, it is nice to let the reader know that's what you're doing. It can be a very jarring step to see if you don't see it coming. dv dt is equal to, that's a constant, pi over 12. The 3 comes down. It becomes a 2. And I want to be done, but I'm not, because the chain rule says I need the derivative of h. Beautiful. Beautiful. All right, I'm ready to plug in. What am I plugging in? Just h, because I solved for r. It's possible that if instead you had all r's in here, you'd have to go back and say, okay, when h is 6, what is r? But we're pretty lucky here. Plugging in, I already forgot, h is 6, and dv dt equals 4. So I get 4 equals, pi over 12 times 3 is actually just pi over 4. Times 6 squared times dh dt. Yeah, the algebra is much easier if you plug in first. You could solve for dh dt and then plug in, but this ends up working pretty well. So, looks like if I bring that pi over 4 over, I get 16 over pi. And then divided by 36, that's that 6 squared, equals dh dt. I guess I can clean that up a little bit. I should get, there's a 4 in each of those, so I would get 4 over 9 pi equals dh dt. Beautiful. We'll leave it nice and exact like that. So It's sometimes worth plugging in and getting a decimal just to see, does it make sense? Does that seem like a reasonable rate? But just knowing how fast the volume is changing and how high you are tells you how quick the height is changing. And notice that the higher I get, the more volume it takes to raise it. At the bottom, a little bit of volume is going to raise it a lot. And at the top, it takes a lot of volume to raise that height because it's getting wider as you go. And that's exactly what this relationship is actually telling you right here. It's saying, oh yeah, as you get higher, the same change in volume is actually going to give you a smaller dH/dt because that h here is going to get bigger to compensate. So that's all embedded in this beautiful formula. All right, that was a lot of steps, a lot of things going on. Definitely worth going back over this real quick. We started by talking about volumes. We did the same game of what is a given rate, what's the rate we want, what is those variables, and what is the and labeling a diagram. If you can get that far, then acknowledge it. Give yourself a pat on the back. You got that far. You did great. It's so important when you're doing this to try to figure out what parts are you actually doing well and what parts are still causing you trouble. So if you got that far, say, hooray, I got that far, and then work on where you got stuck, which is maybe the next step in saying, oh yeah, what is that volume? For a lot of people, the new hitch in this one is that the fastest way to do this is to get rid of this r. And we get rid of this r by recognizing that if I know h, I should know r. And then I had to play this separate similar triangle game, which is not going to go away. Similar triangles are your friend. Okay, so once I got here, my life is pretty easy. I take that implicit differentiation. That may or may not be easy for you still. So if that's the part causing you trouble, you're in luck. We had a whole other section on how to do that. And then finally, the plugging in and differentiating. If you plug in before you differentiate, plugging in and solving. If you plug in before you differentiate, you broke the whole problem. Because now nothing is changing. They're all constants. So you can only plug in these numbers after you differentiate. All right. One last note on this problem before we get before I move on to another one. Let's just say for a second that we weren't so smart, that we didn't solve for r. Then we really could take this v equals pi r squared h times 1/3, and I really could say dv dt equals pi, and now I've got a big I'll pull over 3. Now I've got a big product rule, 2r dr dt. Leave the h alone, big old brackets here, plus r squared dh dt. And now I could try to plug into here. This gets a lot harder because now I've got to try to figure out what on earth is dr dt, which was not one of our givens. So now you've got to back solve for this. You've got to back solve for r. So really not recommended. It is possible. You can do it, and it's a fun little challenge if you think that this is feeling easy. See if you can do it this way. But definitely recommended when you're here to, if you see 3 variables, see if you can get rid of one of them. Okay, that is our last tip. There's a lot going on there. You're doing great. Practice. Lots of examples is actually, in this case, a good thing. But make sure you give yourself the time to think through, get confused, and then try to unconfuse yourself rather than throwing your hands up. All right, I believe in you. I'll see you in the next example.